Hi, I'm Jonathan, and this is an appendix video to our main recorded video for the ITCS 2021 conference about our paper Interactive Proofs for Verifying Machine Learning. It's a joint work with Shafi Goldwasser, Guy Rothblum, and Amir Yehudayoff. And if you haven't seen the main video yet, you probably want to see that one before you see this video. This video is mainly just intended to add a little more detail about the interactive Goldreich-Levin protocols that we used in the paper. Um, so you can find a link to the main video in the description of this video. Okay, so let's start with a refresher about how the regular Goldreich-Levin algorithm works um, before we discuss how to turn that into an interactive proof. So the regular Goldreich-Levin algorithm uh, has query access to some function f from the Boolean hypercube to 0, 1. And its goal is to find all the heavy coefficients of f, all the Fourier coefficients of f that have weight at least tau for some parameter tau. So these are subsets of n, and we need to find all the subsets of n that satisfy this property. And the idea of the algorithm is the following. So if the Fourier coefficient of S uh, has value at least tau, then that means that F is correlated with the character chi of S. So in particular, F the probability that f of x equals L of x is at least half plus tau over 2, where L of x is either the parity of the bits in S or the negation of that parity. So notice that this L of x is a linear function, and therefore if we want to find this L, it's enough for us to find the value of L on all the members of the standard basis, E1, E2, and so on. And why do we want to find L? Because once we know what L is, we know pretty much what F is. So instead of finding F that has the heavy coefficient directly, we're going to find the linear function L that is correlated with F. And in order to do that, it's sufficient for us to find the evaluation of that function on all members of the standard basis. Furthermore, the value of L on a member of the standard basis satisfies this equality, which is that for any x in the domain different from EI, we have the L of x plus EI plus L of x is just L of EI. And that's actually true also if EI is not a member of the standard basis. This is how we're going to be applying it. So we're going to use this equality, and the way we do it is the following. So like I said, if S is a heavy coefficient, then F is correlated with L. And now what the algorithm does is it assumes, and I'm starting with a baby case of the Goldreich-Levin algorithm where it makes this additional assumption. And later on, we're going to remove this additional assumption. So the assumption is that there's some set A, which we will define it later, but there's some set A where the algorithm already knows what the value of L of x is for all the x's in that A, some subset of the domain where we already know L. And using this assumption, which is not a realistic assumption, the baby version of the Goldreich-Levin algorithm works the following. It's going to query f on the value of x plus EI. And then because F is correlated with L, then for many of the x's, it can do the following computation that we said before, which is f of x plus ei plus L of x. And then if, because f and L agree with high probability, then this is with high probability the same thing as L of x plus ei plus L of x, which equals L of ei. So basically what the algorithm can do, because of this, this property, is it can say, okay, I want to know what L of ei is, so I'm going to take the majority over all the bits of the form f of x plus ei plus L of x. So each one of these computations gives me a bit, and for a majority of the x's, I can expect that f of x plus ei will be the same as L of x plus ei, and therefore this whole thing will just most of the time be L of ei, and therefore when I take the majority, I get the correct value. So by querying these f of x plus ei on various x's, I can find the value of L of ei. And then I can repeat that for all the I equals 1, I equals 2, and so on, and learn the value of L on all the standard basis. And that determines the value of L because L is a linear function. Okay, so that's the baby case of the Goldwasser algorithm. Pictorially, we have this set A where we assume that the algorithm knows the value of L on this set, and then it's going to query the value of L, the value of F, sorry, on all the shifts of A by members of the standard basis. So for each x in A, it's going to shift it by E1 and query x plus on F on x plus E1. And then it's going to subtract all of the queries here from all of the values it knows here and take a majority, and that gives it the value of E1. And it can repeat that for E2 and so on. So that's the baby case. Now, let's see how we can use this to define a baby case of the interactive Goldwasser interactive proof. So recall that what we want to do is we want an interactive proof where the verifier only uses random samples, and the prover is the one that can do queries. The prover has query access, but the prover is possibly malicious. We can't trust the prover. So the verifier is going to basically simulate the Goldwasser algorithm, and whenever it needs to query something, it's going to ask the prover to do the query for it. It will say, please query f at this x and tell me what the answer was. And somehow it needs to make sure that the prover is not cheating, and that the answers the prover is giving are actually the correct evaluations of f. So again, we're going to have this assumption from the baby case, which is that the verifier knows the value L of x for all x's in some subset A of the domain. And we're going to, in the next few slides, we're going to define what A is and going to eliminate this assumption. Okay, so like I said, we're going to, okay, so in order to catch the prover and make sure that it's not cheating, what the verifier is going to do, it's going to use its query access in order to get some samples of the form x and f of x for random x's, and it's going to hide those x's inside A plus ei star for some randomly chosen I star. And then if the prover is dishonest, then it will get caught because it might give incorrect answers for things that the verifier already knows what the answer is, and then the verifier knows that the prover is lying. So how does this work? The verifier chooses a random index I star between 1 and n, and then it defines A to be the samples that it took. It takes samples x1 till xm, and then it shifts all those samples by ei star. So that's the definition of A, and that means that now the samples are basically the set A plus ei star. All of these pluses, maybe I should have said this earlier, all of these pluses are XOR. So adding and subtracting is the same. Okay, so that's A. And now the verifier queries P for the value of x plus EI for all x's in A and all the indices I between 1 and n. And the claim is that if P is dishonest, if P lies about even a single evaluation of F, then it will get caught with probability at least 1 over n. Why is that? Well, because I star is a completely uniformly random index. And so the probability that the prover lies on a query that belongs to A plus EI star is 1 over n. The prover doesn't know what I star is. And if that happens, if it lies on a member of A plus EI star, then it gets caught because the verifier knows all the labels for the samples it took. So if the prover is dishonest, it gets caught with probability at least 1 minus n. And if it's honest, so if it gives the correct evaluations for all the x's it's queried on, then the verifier is just running the Goldwasser algorithm proper, the way it should run, and therefore it will find the right function L and find the right set F and so on. So that's the baby case of the interactive protocol. And now what we want to do is we want to remove this assumption. So yes, we have this set of samples that we took, and by shifting it, we define this set of samples that the verifier took to be A plus EI star, and therefore A is just the shift of that. And by EI star, not E2, the way it's written here. And then we still had this assumption that the verifier somehow magically knows the value of L on all the members of A, and that's not a realistic assumption. So in order to remove that assumption, what we're going to do is the following. Instead of A plus EI star being the samples that the verifier took, the verifier is going to take a relatively small number of samples, something that is logarithmic in n. So we're working with the function f from the Boolean hypercube, which is 0, 1 to the n. So now we're taking a number of samples that is logarithmic in n. So those are these green dots here. And then A plus EI star is going to be the span of the samples that the verifier took. So the verifier takes those samples, sees what the span is, and then it's going to figure out what A is just by shifting by EI star. And then it's going to choose a random basis for A. And it's going to send that random basis of A to the prover. And that's basically telling the prover, here is the set A that I chose, and this is a description of A, and the basis of A defines A. A is a subspace of the domain. And then the verifier is going to do some brute force over the values of L of AJ. And I'll explain that in the next slide. So more fully, the verifier takes m random samples, with m being logarithmic in n, and it defines A to be the span of these random samples shifted by EI star. And it chooses a random basis A1 till AM of A and sends that to the prover. And notice that the value of L, previously we assumed that we know L, the value of L on all the x's in A. So notice that the value of L in A is defined by the value of L on this basis, A1 till AM. Because L is a linear function, so once you know its evaluation on all the AJs, and each x is just a linear combination of AJs, then the value of L at x is simply the linear combination of the values of the L AJs. So what that means is that because m is logarithmic in n, so there's only a logarithmic number of members in this basis, a1 till am, then we can iterate over all possible assignments of values Laj for all aj. And iterating over a polynomial, all the assignments for polynomial numbers of bits is logarithmic. So in logarithmic time, we can iterate over all of the possible assignments Laj for all for all the members of the basis. And for each assignment like that, that defines one possible value of L. And so there's only a polynomial number of possible L's that need to be considered. And so we can just, what the verifier is going to do, it's going to query f on a plus ei for all the i's as it was before in the baby case. And then when it gets those queries, instead of knowing what the value of L is on A, it's going to just say, okay, if the value of L was this, then I'm going to get this heavy coefficient. If it was that, then I'm going to get this heavy coefficient. And it only has a polynomial number of suspected heavy coefficients when it works this way. And so instead of outputting coefficients that are definitely heavy, it's going to output coefficients that are suspected as heavy. And then the total number of coefficients that it's outputting is at most polynomial in n. So the output is going to be a set of coefficients that includes all the heavy coefficients, because in particular, we're working with also iterating over the correct value of L, and also the list of heavy coefficients will contain some coefficients that are not heavy, but that is not a problem for our purposes. So this is how it looks again. We have our logarithmic number of samples. We look at the span of those samples, and that is a plus ei star. Then the verifier sends a random basis of A and to the prover, and then the prover will give the verifier the evaluation on A plus E1, A plus E2, and so on. And then the verifier subtracts those evaluations provided by the prover from all the possible values that L could have on the set A, and that's only a polynomial number of possibilities. So to complete the proof, we have a few last things we need to notice. So first of all, like I said, including a polynomial number of non-heavy coefficients in the list that is output by this interactive protocol is okay. And the reason is that what we're going to do with this list of heavy coefficients is we're going to use it in the Kushilevitz-Mansour algorithm to estimate what the function, we're going to estimate each one of these heavy coefficients, and that will give us an estimate of the function f. And basically, like, the more coefficients you estimate, the better your estimate of f is. So we don't mind so long as this list is polynomial, and therefore we can actually estimate all of them with good accuracy and so on. So these additional non-heavy coefficients don't cause any damage. The next point we need to take care of is that you need to be sure that the prover can't somehow know which are the decoy x's and which are the actual x's that the verifier doesn't know the value for. So how can we be sure that the prover can't somehow figure out which are the samples and which are the actual queries? And basically, the reason for that is that when the verifier takes the random sample, which is logarithmic in size, and with high probability that random sample is going to be linearly independent, and that means that it's basically going to be some random basis of A plus EI star for some random I star. And that means that, in particular, each x that the prover is required to provide an evaluation for is equally likely to be a decoy, just as equally likely as all the other x's, because like each member of a subspace is equally likely to be a member of a random basis for that subspace. And so the prover can't decide to, lie in some clever way only on x's that are less likely to be decoys or something like that. And finally, you need to do some additional calculations to see that if the prover is dishonest, then it will get caught with high probability. And what I mean by that is, so if the prover, let's say, lies about only one evaluation, then it won't get caught with high probability. But we also don't care because remember that what the verifier does is it queries the prover on, a plus e, a plus e1, a plus e2, and so on. And for each I, it takes a majority over all those queries, and that's a big number of queries. And because f is correlated with L with probability, half plus tau over 2, then there's this advantage tau over 2. So it's not enough for the prover to be dishonest in one query. It needs to be dishonest on enough queries in order to flip what the majority would be. And so the prover, in order to manipulate the output of the interactive protocol, it needs to be dishonest on enough of the on a fairly substantial portion of the quiz in order to flip the majority of at least one of the EIs. And then you need to do a calculation to show that if it is that dishonest, then it will get caught with high probability because we chose enough random samples. We hit enough random samples that will get caught with high probability. And in order to do that, you also need to repeat this protocol a number of times independently, basically to amplify the probability of catching the prover. But these three bullets basically wrap up the explanation of the interactive Goldwasser algorithm, and that's it. We thank you for watching, and we will be happy to answer questions during the ITCS conference on the Slack channel that's dedicated to this paper. Thank you very much.